It's giving some ideas also. So first of all, the concept of the heat flux. What do we mean by the heat flux? So heat flux, here in this graph, if you are taking it, the heat transfer is occurring due to the temperature difference. This thing we have understood. Heat transfer is taking place due to the temperature difference. Now, in a spatial coordinate, if you are considering here one, this is one solid plane wall. We are considering one solid plane wall. Yes. Plane wall. In this wall, that is the one side of the wall, this is the other side of the wall. 3D, we are not taking into consideration, only one dimensional we are taking. First, we are considering, for the sake of the easiness, one dimensional case. So, one dimensional case, so this surface and this surface. This is one surface of the wall, this one surface of the wall. This surface having a low temperature, let you take it is a, and this surface is having the high temperature. Two plane surface, this surface having a high temperature TH, this surface having the low temperature TL. So heat flow will take place because one side higher temperature, one side lower temperature. Heat flow will be takes place from higher temperature to lower temperature side. So direction of the heat flow. What is the direction of the heat flow? The direction of the heat flow is in this. That is the direction of the heat flow. So heat flow is taking place from higher temperature to lower temperature. T, this is a one-dimensional case only considering, so let you take it is the X along X-axis. Heat transfer is taking place along X-axis. Heat transfer is taking place along X-axis. In heat transfer subject, we are talking this Q, we are considering that is rate of heat transfer. In thermodynamics, Q is the heat transfer, and that is the rate of heat transfer. That means per second, how much heat is transferred. So what is the unit should be there? Joule per second. Or we can say it is the watt. That is the unit. Q is the unit. Rate of heat transfer per second, how much amount of the heat is flowing. That is the Q. Now concept of the heat flux is coming. What does it mean by the heat flux? Heat flux concept is coming. So temperature here it is higher. TH, let you take here some other color I am using, it will be easier to understand. So let you take in this here, this side the higher heat, TH, and this side is the lower temperature. Here higher temperature TH, here lower temperature TL. And because of it, heat transfer is taking place. Because I am plotting this temperature in this graph. I am plotting this temperature in this graph, and here the temperature to, so is coming in this. So T at any point X, at any point X, that you take it is X. At any point here temperature, what is that? This temperature is nothing but a T. That temperature is T. And T temperature is a function of X only. Only X. one-dimensional case we have considered, temperature is the function of x. This curve, this temperature is the function of x. So in that case, this heat flux concept is coming into the picture. How it is coming? T is a function of x. So what is the dt dx? What is the dt dx? How we know it is the dt dx? So dt dx in the form of the integration, if you take one small elemental from the plane wall, if you take one small elemental area, that is a small elemental area if you take, and one side there is a temperature, this side may be the temperature T, this side may be the temperature T plus T. Because this side higher temperature always, left side, because here already higher temperature, that's why heat flow is occurring this side. Q is in this direction. Then only Q will be in this direction. This side higher temperature, this side lower temperature. So why this heat transfer is taking place? dt by dx. This is the temperature gradient. This temperature gradient is causing the heat transfer. This temperature gradient is caused for the heat transfer. And this heat transfer Q is directly proportional to the dt by dx, temperature gradient. Because we are considering it is not a linear, it's a non-linear. dx is not linear, we are considering. In the case of the non-linear, let you take it as a non-linear. It may be linear. It may be linear, it may be non-linear, does not matter, but that's why dt dx concept we are taking. If it is a linear, no problem with it. Simply we can write it down. If it is a linear cases, we can write it down th minus tl divided by this total length. If it is L, so L. If it is a linear. As it is a non-linear, in terms of differential form, we are writing it. Instant, at any instant, what is that? So that is the case. So for general cases, we are taking it non-linear. That way, simplification will do it as a linear. Okay. So this heat transfer, rate of heat transfer is depends on the temperature gradient. And another thing, it is depends on one more things that we are going to discuss now. That is the area, cross-sectional area. Very, very important. Cross-sectional area normal to the direction of heat transfer. This is the most important thing. This Q, heat transfer, is also proportional to this A. At any section AX, if you're taking AX at X, AX. So this Q, rate of heat transfer, is directly proportional with the temperature gradient because it is the cause. This temperature gradient is the cause. Due to the temperature gradient, it is the cause, is the effect. That's why it is known as the Constitutive Law. This law, what we are going to discuss till now, that law is as a constitutive law. Here the cause and effect are interrelated with each other. And as well as this heat transfer is depends on the cross-sectional area which is normal to the heat transfer. So in this area at X, in this case the X at X here, this cross-sectional area, if you consider this area which is normal to the heat transfer. This is the AX. It is depends on this area. So Q is a proportionate with the dt dx, Q is the proportionate with the AX. So we can say the Q is proportionate with the AX into dt dx. Hence, for the sake of the equality, Q is equal to KAX dt dx. K is the proportionate constant. One constant is very, very important. This is the thermal conductivity. It's a property of the system, thermophysical property of the system. This thermal conductivity is nothing but a thermophysical property of the system. Thermophysical of the system. So what is heat flux? This heat flux, now we are taking this heat flux, the concept of heat flux we are talking about, this is nothing but this rate of heat transfer divided by the cross-sectional area normal to the heat transfer. That is the heat flux. So along x direction, heat flux is Qx. Rate of heat transfer divided by the area normal to the heat transfer. So that is the concept for the heat flux. So again, we are rewriting this thing. We are giving a very good conclusion till now. What we are getting it. First, we are recap. So Q, heat transfer, is proportionate with the temperature gradient, which is the cause for the heat transfer. Heat transfer proportionate with the area, cross-sectional area, which is normal to the direction of the heat transfer. Then we got it, one KAX dt dx. It's a very, very important equation. This is known as the, I'm coming one more things. Here, I forget to tell it is the minus sign. Sign will be minus in nature. Why? Because you can see in the direction of heat transfer where it was, in the direction of the heat transfer was in this side. That is the Q direction is in this side. Temperature decreasing. Along the heat transfer direction, temperature is decreasing. So if you go positive X side, if you go X positive side is this side. So you will see the temperature is continuously decreasing. So temperature is continuously decreasing. If you go positive X direction, you will see the temperature is continuously decreasing. So this dt dx with minus side or negative sign is the cause. Temperature should reduce along the direction of the heat transfer. This thing you have to keep in your mind. Temperature should decrease. In a spontaneous process, temperature should decrease along the direction of the heat transfer. So here, one minus will comes into it. One minus sign will come there. This law is given the heat conduction law by James Fourier. Sorry, Joseph Fourier. Joseph Fourier's law of heat conduction. This one thing is enough to remember for the entire subject, entire conduction. This one thing is enough to remember. I am repeating this thing because if this thing is clear to you, the total heat conduction scenario is clear to you. So, heat flux concept, what are you telling? Heat flux concept along x direction. What is the heat flux? Heat flux is the Q, rate of heat transfer divided by the Ax. So that will be equal to the minus Ax. All the case we are talking about, all the case we are talking in one-dimensional cases. So heat flux, that is the heat flux. So heat flux is nothing but the heat transfer per unit area, which is normal to the direction of the heat flow. So the area, normal direction to the heat flow, that is a vector quantity. It is a vector quantity. This is the vector quantity, heat flux. If you remember the similar kind of the quantity, the stress. The stress, you will see, it is a tension. It is not a vector, it was a tension. Because stress may be happen in any orientation of the area. It may be normal, it may be horizontal, it may be inclined, anywhere. If area orientation is not vertical, horizontal, inclined, anywhere stress can be there. Stress will be there. But heat flux only consider the area which is normal to the direction of the heat flow. So it is defined. Area orientation is defined. Direction of the area is defined. So that's why it's a vector quantity, whereas the stress was a tension, second order tension. So that is the difference between heat flux and stress. So over the area, over the cross-sectional area, everywhere, let you take, there is a cross-sectional area, let you take here. This direction, we are not taking the, at x is the x, small x. At x, the qx, there everywhere, qx might be there, qx, heat flux. It may be constant, may not be constant. Because it may vary with y direction, z direction, it may vary. It may vary over the cross-sectional area, y and z is changing. So qx may be constant or may not. Or may not. It's a vector, first of all. We are talking about a point. We compressed it in a point. It may be constant, it may not be constant. Because if you come here, in this case, it is better to define it. If you take one point here, over the point, there may be the heat flux. Heat may be going around this direction. Heat may be going around along this direction. Heat may be going this direction. So heat flux along this is the x direction. This is the Y, the Z. So heat flux in this side Qx, this side Qy, this side Qz. From a point, all around heat is going. Very high temperature in that point. So heat is going in different direction with different amount. It maybe happens. Along x direction, it is going a different value. Along y direction, it is going a different value. All are the vector quantity. So Qx is happening. Qx, what is the Qx? Heat transfer along x is a per unit area normal to the direction of the heat flow. Similarly, this one also. Some Qy is going, let you take, and Q1. And this is the Qz is going this way. So entirely here, the total heat flux Q, the total heat flux Q is I of Qx of Qy, so this is not a vector, and here magnitude and direction we are showing it here is the magnitude. So Q is a I of Qx along x-axis, along y-axis, along z-axis. So what is the Qx? Qx magnitude, we have seen it. That is the minus k. In that case, del T del x. Because temperature is a function, three-dimensional case we are considering x, y, z. So there is a three component will be there. Temperature changes along x-axis, temperature changes along y-axis, temperature changes along z-axis. This is the cause for the Qx. This is the cause. This is because of this. That is the cause for the Qx. This is the cause for the Qy. This is the cause for the Q. So in that case, we can write it down minus k del T. And here Qz is equal to minus k del T. So ultimately, what is happening? The total heat transfer is equal to minus k, if you take it common everywhere, I del T del x plus k del T del y plus k del T del z. So it can be written as the k grad T. This is the Joseph Fourier's equation of the heat conduction in three dimensions. These are all around. Actually, it is given by the Joseph. Previous consideration was the one-dimensional case. This is the actual cases. Because grad operator is I d by dx plus j d by d del y k del y. So in three-dimensional cases, the heat flux can be written in this way. That's what way we are writing it. We are writing it here. The vector quantity heat flux is equal to minus k this is the equation. It is valid for everywhere. For the case of the Cartesian coordinate, cylindrical coordinate. It may have had for the spherical coordinate, everything. So that is the basic general thing. So heat flux, and temperature gradient. In between which is creating the bridge? The bridge is created by the K. K is known as the thermal conductivity. This thermal conductivity is creating the bridge between the cause and effect. This heat flux is the effect, and it is the cause. This law is known as the constitutive law. This law, Joseph Fourier heat conduction law, is known as the constitutive law. Like another constitutive law, stress versus strain. Hooke's law is a constitutive law. Newton's laws of viscosity is a constitutive law. The similar. It relates between the cause and effect. It relates between the cause and effect. So that's all regarding this. Next, we'll talk about some slide between the thermal conductivity.